Okay, so let's talk about the alternating series test here. So with the alternating series test, you have to remember an alternating series is one in which all of the terms switch back and forth amongst the signs. So positive term, negative term, positive term, negative term, positive term, negative term. And if you have two consecutive terms that have the same sign, it's not an alternating series. So the alternating series test is useful because we run into alternating series quite a bit, and alternating series are very, very well behaved. So the rule is here. This series converges if all the following are satisfied. Each a sub n is positive, a sub n is greater than a sub n plus 1 for all n greater than some integer n, and the limit of the terms goes to 0. So super quickly, unless we talk about these rules, they'll be a little confusing. So this first one says that each a of n is positive, a sub n is positive, which makes it sound like it's not an alternating series. But if you look at the way the series is expressed, it has this -1 to the n already included in its definition. So what this really means here is that the a sub n isn't going to affect the sign that the -1 to the n causes. So it's going to alternate because the -1 power is going to go back and forth between even and odd. So this assures that it's alternating. Now, the second statement, a sub n is greater than a sub n plus 1, this means that the terms, the actual magnitude of the values, is always decreasing. And then this part at the end, for some n greater than n, for some integer n, that looks confusing. What that basically means is that you could ignore anything that happens in like the first few terms as long as the series eventually gets to this point where the terms are always decreasing, then it fits this pattern. So if I had like the first 3 terms weren't constantly decreasing, but every term after that was, then this capital N would basically be like 4. So after the 4th term, everything decreases. So we would say mathematically that this happens eventually. So you can ignore the first few terms as long as it happens eventually, we're good. And then the last part, which is the part that we tend to use the most often for the proof itself, once we look at the first two things, the actual math part of the proof, is that the limit of the terms themselves, once you ignore the -1 to the n, the alternating part, has to go to 0. Now, so that's the alternating series test, 3 parts. It has to alternate. The magnitude of the terms has to be decreasing eventually, and then, consistently decreasing eventually, and then the limit of those terms has to go to 0. So let's look at a couple of multiple choice exams that are from your packet. So here's the first one. So I'll let you find that in your packet. Pause the video if you need to. All right, so we're going to look at the alternating series test. So the first thing is that the terms actually have to alternate in sign. So if you look at the first series, we go from positive, negative, negative, positive, negative, positive, negative. So yes. Second series, yep. Third series, yep. So the first condition is satisfied. The series are all alternating. The second condition is that the magnitude of each of the terms has to be getting smaller consistently as we go along. So if I look at the first series, you see how it goes from 4 to 1/9 and then back to 1? So that's a smaller, then a larger, then a smaller again, then a larger, smaller, larger. That's not actually consistently decreasing. So that means the second condition on this one is not satisfied. So that one gets ruled out. If you look at the second one though, 1, 1/2, 1/3, 1/4, 1/5, yeah, those consistently decrease. And 2/3, 3/5, 4/7, 5/9, 6/11. You may actually have to pull your calculator out to make sure that happens, but it does. Those are consistently decreasing as well. So then there's the third part, which says the limit of the term, when you ignore the -1 thing, has to go to 0. So if you look at the second series here, the limit as n goes to infinity of the term itself and ignoring the -1. So that's basically 1/n. Has to go to 0. And that does. So this second series satisfies all three conditions. If you look at the third series though, when I take the limit as n goes to infinity at the stuff and ignore the alternating part, you can see from L'Hopital's rule from highest degree terms, this goes to 1/2. That doesn't go to 0. So we would consistently be adding something to the series. So it basically is not going to approach a single number. So the only one that satisfies the alternating series test here is 2. So let's look at the other problem in your packet that also has an alternating series test. And this one's a little more straightforward. It basically says which of the following is true about this series. So the easiest way to see what's going on with any of these things, if you're given a general term, is to write out the first few terms. So I'm going to write out the first few terms here. I start at n equals 2. So my top on the first one would be this. And then 3 would give me this. And I could write out a few more just to make sure that I'm understanding what's going on. One more. And so forth. So if you look at this, the first statement says the series is alternating. So if you look on top and bottom, the tops definitely go back and forth between 1 and -1. And the bottoms, square root 2 plus 1, square root 3 minus 1, square root 2 plus 1, square root 5 minus 1, those are all positive numbers. So the fractions are going to go back and forth between positive and negative. So that one is true. The second statement says that the terms are consistently decreasing. So if you were to look at this, square root of 2 is about 1.4. And then the square root of 3 is like 1.7. And then this is 1/3. And then this one, square root of 5 is like 2.2-ish. You can clearly see, even if you ignore those negative signs, the denominators are going big, small, big, small, big, small. So the whole fractions are going small, bigger, small, bigger, small, bigger. So those are not consistently decreasing. So that one isn't satisfied. And then for the third part, we have to look at the limit as n goes to infinity. Now, when you look at this, I'm going to go ahead and consider for a second the -1 still being in there. Remember that we look at highest degree terms on things when we're looking at n going to infinity. So if I were to look at the absolute value of this whole thing, the thing on top would act like 1. The thing on bottom, because you're adding and subtracting that number from the square root of n, wouldn't always look like the square root of n plus 1. However, if you look at that bottom, square root of n is going to be way more powerful than just -1 to the n. As n goes to infinity, that's going to get infinitely large. -1 to the n is just going to be either 1 or -1. So the highest degree term on the bottom will be square root of n. So that limit is going to go to 0. So that part's satisfied. So 1, 2, and 3 are satisfied. The alternating series test comes up a decent amount, especially on the multiple choice parts. So remember, has to be alternating series. The magnitudes of the terms must be consistently decreasing, and then the limit of the terms must go to 0.